Okay, so the purpose of this video is to provide a very quick overview of the process involved in creating a light curve of Didymos. This is the asteroid system that has Didymos and Dimorphos that has been in the news lately. So I'm going to go ahead and get started here. I first start off with the image manager. So what we want to do is go ahead and populate with a list of images. So in this case, these are images taken from iTelescope T72 in Chile. And I'm just going to go ahead and load these up here. And the next step is to specify your observatory setting. So if you're new to Tycho, if you've never set it up before, I would actually probably recommend you watch another video on the first time setup. But I'm just going to go ahead and point out here, you'd go to Settings, Observatory, and you would configure your observatory configuration. So in this case, I want T72, that's iTelescope T72 in Chile. And I'm just going to show you here what that looks like. So Observatory Info, I can give it a label. I've already done that here. Observatory Status, so if you already have a Minor Planet Center code, you could choose that. If you are applying for one, you could choose that option. Or if you do not have one, if you're a temporary roving observer, that's what they call that. That's actually the case here. So iTelescope, they do not yet have an MPC code for this observatory. So you just go ahead and give it the longitude and the latitude, basically the location info. You can give it the design type. What is it? It's a reflector, 0.5 meters. So you can give it all that information. You can give it the camera info here. So how does it refer to the date in the image? So the date obs. Timestamp refers to beginning of exposure. All this information, it's in the user guide, so I don't want to go over too much of that for this particular video. But ultimately what you're doing is you're just going ahead and specifying what observatory captured these images. So once you've done that, you can double click on that in the list and you'll notice it updates over here. So that's the observatory that captured these images. Next step, what we want to do is go to Action menu, and I can choose Express mode, and this allows me to choose a number of steps to be done one after the other in sort of automated fashion. So I'm going to do Calibrate, and in this case iTelescope already calibrates the images. They already have a dark frame and a flat frame, so I'm not going to use those, but I am just going to choose Fix Hot Pixels just in case there are any hot pixels left over. It basically just looks at all the images in the set and identifies what pixels might be considered a hot pixel. So I click Save Settings there. Alignment, plate solving, those are the only other two things I'm going to do. Alignment, I'm just using internal alignment, and bicubic interpolation, automatic downsampling. Again, all this stuff is in the user guide, so if you want to learn more, you can about that, but that's pretty straightforward. Plate solving, I'm using the online solver, which is actually very quick because it does not actually upload the image data. It just uploads extracted sources. And I give it the lower and upper bounds on the plate scale, so you do not have to know the exact plate scale of your images. You can just say, maybe it's from 0.2 to 5 arc seconds per pixel. So that's a pretty wide range. So 0.2 is very oversampled and 5 arc seconds per pixel is very undersampled. And downsample factor of 2, standard extraction. Again, you can learn more about it in the user guide if you want to know more detail if you want, but these are the settings I'm using: calibration, alignment, and plate solving. So go ahead and click Start. So again, this is kind of the pre-processing step involved. So I might even be going into a bit more detail than you care about for this kind of video, but just kind of giving a little bit of a start to finish of what this looks like if you're new to Tycho. So it's already finished the calibration step, so at this point it is doing the alignment phase, and Tycho is aware of GPU acceleration, so if you have a GPU, then that can speed things up, so that's what I'm using here. So OpenCL device selector, you can just see you have options for that. If you do not have a GPU, that's perfectly fine. That it works great in what I call CPU only mode. It just runs a little bit slower, but it still works just fine. So at this point, it has now finished the alignment step. So now we're on to the third and final step of what I call pre-processing, which is to do the plate solving. So it has uploaded extracted sources. Now it's doing a solution. So it says the solution has been found, and now it has finished that. So it says it has been plate solved. These are the resulting images. Now, if we want to, we can go to Action, View Images. So this is going to let us see what this data set looks like. So I'm zoomed in a bit here. I'll just zoom out some. So this is what that field looks like. And you might be curious, well, where is the object? Well, there's a couple ways to answer that question. One is you could go to File, Load Known Objects, and it would give you an overview, or also an overlay of all the known objects in the field. That's one way to do it. Another is if you're just working with one object that you care about, you can go to the Image Manager and choose the Ephemeris pull-down menu here and choose Attach from JPL Horizons. There's also Attach from Find Orb, which is another great software, but for this purpose I'm just going to use JPL Horizons. I can reduce this window size here a bit, and you give it a target identifier. So in this case, I already know it has number 65803. If you didn't know what the number was, you could look it up, but here we just know it is 65803. And I'm going to choose Ephemeris attached to dataset. So what it's going to do here is it's going out to the JPL Horizons service, and it's saying, I want to know all there is to know about this object for every single image. So again, there's 186 images here. So I know, for example, if it's in the field of view, I know its coordinates, I know its magnitude, speed, position angle, and so forth. And another nice thing here is that now that I've attached that ephemeris information, anytime I click on an image, it'll automatically center it in the image viewer. So here is the object of interest. As you see here, as I scroll through the list, it continues to track that object. So that's kind of nice. Now, if we're doing photometry here, if we're trying to construct a light curve, we'd want to know what is a good measuring aperture for this object. So I'm going to choose this menu here, photometry menu. Again, I'm in the image viewer, so I go to photometry menu and I choose modify aperture settings. And this brings up another window here, and I already previously identified an optimal aperture, but in case, if I just click on defaults, this is what the default setting looks like. And you can see that that inner radius is a bit too small with the default. So all I have to do here, I'm working with a circular aperture. I can adjust these sliders back and forth, and I want to say that this looks like a pretty good, as I enclose the object here in this inner radius, that looks like a pretty good setting here, 9.5. So I could choose that option and click close. And now what I'd like to do is I'd like to go ahead and identify what would be good comp stars. Now before I do this, again, if you're new to Tycho, you probably need to set up your star catalog. So I don't want to go into all the details on that for this particular kind of video, but you go to settings, star catalog, and I like to use the Atlas catalog because it's a very good catalog for photometry. If you go to the Atlas tab here, it gives some info about this catalog, and it's good for high precision photometry. So again, feel free to read more about that if you want to, but these are the kind of settings I'm using. I'm using the Atlas catalog. And so again, I mentioned comp stars. We want to do differential photometry. So I'm going to identify comp stars to do the differential photometry here. So this brings up a new window. It's called Comp Star Finder. And what I like to do here is I like to choose comp stars that have the same kind of color index that my target has, or at least I should actually say, especially for asteroids, solar type comp stars. So you can do that pretty straightforward. You can have a min and max for the B minus V here. And again, these are kind of like the default settings. But I'm just going over here to the trend line, and you can see that if I click on one here, it'll go to it in the image viewer. Now, all I have to do here, I'm just doing a first pass. Okay, so I want to construct a list of comp stars. It doesn't have to be perfect at first. Again, it's just a first pass. So I'm actually just going to go through this. Here I'm going to right click on every single one of these points that I care about and choose Add to Active Comp Stars. So the first one there, it brings up a new window, Active Comp Stars. And I just keep on doing that for these data points that are nicely on the line here. Now if I mess up, if I add one that's already been in the list, it's no big deal. It just says, oh, it's already in the list. So just keep on doing this here. And again, I'm kind of choosing comp stars that have somewhat of a similar magnitude as that of the object. I happen to know the object magnitude is around mag 14. I could actually choose some that are mag 13, and I already did. It's already in the list there. I probably don't want one that's mag 12 necessarily. I could try that if I want to, but you definitely don't want ones that are saturated. So if they're too bright, they could be saturated, and you don't want that for your comp star. Anyway, I've got 12 comp stars in my list now, so I'm going to go ahead and choose Graph Generate Data. So I do that, and it's going to populate. After a while, it's going to construct a trend line for every single comp star. And the idea here is we want to find comp stars that have a nice flat trend line. Now this one's got a little bit of noise in it, but again, I mentioned this is kind of a first pass. So what we want to do is just identify. I like to start with the one that's the worst in the list here. This one looks particularly bad. It's actually at the edge of the field of view. That's why it's not so good. So I go ahead and right click, choose Remove Comp Star. So I just start to cull the list down here, and I find the next worst one in the list, maybe that one. Remove that one, that's fine. This one's got a lot of scatter as well. This one is also not too good. And now I'll just go ahead and regenerate the data. And I've kind of reduced it a little bit. So go ahead and give it a moment to complete that. So these look pretty good. Again, it's perfectly fine if you've got just a couple of outliers on one or two. I might remove this one here. That's fine. And so this would be my list of comp stars. Now if you want to, you can actually save this list, and that'll allow you to import it later. So I go to File, Export, and I could just call it comp stars. In fact, I've already done this before, so I click Save. So that allows you to import later if you just want to make sure you use the same comp stars. For now, the next step is, now that we've identified our comp stars, we've identified the optimal aperture. Now we want to go ahead and create measurements of our target. So again, recall that we've actually attached ephemeris information of the target. So I've mentioned in previous videos that you had to define marker 1 and marker 2 to define kind of the motion of the object. Well, because you've attached ephemeris information, you don't actually have to do that. In fact, you can just go, all I did here is I right-clicked, this brings up a pull-up menu here, and I choose Create Photometry Ephemeris. So it actually is just going to use the ephemeris information that's been attached to every single image to understand what needs to be measured. So it's already finished. We've constructed one photometry set of 186 data points, one for each image. And if I want to, I can go to Graph, Plot All Sets. There's only one set here. Now you'll notice this looks pretty good, but it's got a little bit of scatter here. So now I will say this, if you don't see anything at all, go to your graph settings and choose floating for the magnitude range. What that's going to do is, if you happen to have any outliers in the data, it'll scale that vertical axis so that you see all of the data points. But in this case, and in fact ideally, you pretty much always want to choose fixed range whenever you've got it finished out, because fixed range is what the standard is. You typically want to do a fixed range of 0.8. In this case, it is a somewhat low amplitude object, so I'm just using fixed range of 0.6. That may be a bit too much detail for this video, but you can kind of get the idea. So I do notice there's a little bit of scatter here in this data point, so we can click on it, and that actually will take us to where that is in the image viewer. So if I zoom in here, and again I'm at this list of photometry measurements, if I go back and forth, you can see what happened as the object passed in front of a star. So that being the case, we had a little bit of interference. Not a big deal, it's pretty straightforward. I can simply say that I want to identify the start and stop. So it looks like number 129 to 134. So I'll go ahead and delete from 130 to 133. So I select those and choose delete. Having done that, that removed the scatter from this raw plot here. Now the next thing I want to do, back at the photometry sets, you have this kind of this navigation bar at the top. So I'm going to photometry sets, and I want to apply object data. So what that means is I right click on the photometry set and choose apply object data, and I can do a search. I happen to know that number of the object is 65803. If I didn't know the number, if I just knew its name, Didymos, I click search for that. Either way, it's going to pull up the object information here. Just select it, click OK, and you give it a moment, and as you see, what it has done here is it has populated all of these columns, all of these columns here of information. So we have, for example, phase angle bisector, we have the air mass, we have the altitude of the object, sun target distance, Earth target distance, all of these quantities that can be used to determine things such as light time correction. That's useful for asteroid photometry. Also H minus G correction. So I go back to graph, plot all sets here. You notice in the magnitude menu here we have H minus G correction is now applied. We also have light time correction is applied. So these are all things that are useful when working with asteroids. So at this point, if we wanted to understand that this is just one night of data, but if I wanted to, I could go ahead and go to period, find period, and then try to see if it could find the rotation period of this object. Again, this is a somewhat of a challenging object because it is spherical, meaning it has a low amplitude, meaning that you have to have good SNR on the object. But in any case, I'm just going to specify a start and stop of the rotation periods from 2 to 5 hours, and I'm going to go ahead and click find period. If you're not sure about all these settings here, again, the user guide has more info on that. So it came back with the first candidate here, 2.24 hours, and that's pretty good for just one night of data. That's not exactly the 100% in agreement with the published value because, again, it's just one night of data. You'll know if you've done asteroid photometry before, you typically need multiple nights of data to zero in on the correct value, which in this case is supposed to be 2.26. So we had 2.247. That's pretty close. But again, more nights of data will help. So let's go ahead and see what that looks like. And I'll just do that real quickly. So in this case, I'll just go ahead and go back to the image manager, reset and clear. And what I should have done is I probably should have saved that set. And in fact, it's already here. But I'll go ahead and go to File, Save to Repository. So again, I want to save that set as a test 65803. -1, that's fine. And so I've saved that night of data. Again, what I'm going to do here is do one more night of data. I'm not going to go through all of the pre-processing, so I'll just go ahead and load up calibrated, aligned, and everything. So I do it in place solved just to make this quicker. So you can start to see this process. So again, I can attach ephemeris to this data set. So it's done that. We've got every single image here. There's 193 of them in this particular set. Good action, view images. So we'll give it a moment here. The observatory is the same. These images were also collected from iTelescope in Chile, so I don't need to change my observatory setting. So here's what this looks like. And again, I've attached the ephemeris information. So this target tracks quite well. And so what we want to do, again, I mentioned, first step, validate your aperture settings. So again, I went to photometry, modify aperture settings. That still looks pretty good to me, 9.5. If I wanted to, I could change it a little bit. This is just another night of data. There's going to be an offset anyway, so I go ahead and do, maybe I want 8.9. That looks pretty good. So I click close, and again, now I've done that, I want to do comp stars. I want to find comp stars in this field. So as before, I just go ahead and populate a list of 10 or 11 just to start with. So I'm just going here pretty quickly, and we'll see what that looks like. There's 9 comp stars in this list. So again, first pass, I identify the comp star that looks the worst, and I'll remove it from the list. So I probably want to remove this one, and maybe I'll even remove this one. Those were ones that had a little bit less signal-noise ratio on them. And I'll go ahead and regenerate the data. There's not as many comp stars this time. You notice this is a somewhat small field of view, just 29 or just 26.9 by 21 arc minutes. So the smaller the field of view, the fewer comp stars you're probably going to find. So just keep that in mind. So that looks pretty good. Again, if I wanted to, I could save these comp stars, but I'm not going to for this video. Now, what I want to do is, again, we've done our aperture setting, we've done the comp stars, and now I want to make measurements of the object. So right-click, create photometry ephemeris, and it's generating all those measurements, 193 of them, one for each image. And I'm just going to go to graph, plot selected. So I'm only going to plot just this one set here, just this one night, not both of them. And I'm going to make sure it looks good. So this is again a raw plot of the data. And again, I'll remind you, if you don't see any data here, that might be because you have some outliers that are outside the vertical axis. If that happens to you, go to Graph Settings and choose Floating. So that's just going to adjust that vertical axis. In this case, it actually made the vertical axis where it looks like you're zoomed in. And that's because we are in fixed range. And again, this is a small amplitude object. So a range of 0.6 was actually zoomed out somewhat. But again, you're supposed to use a fixed range if you're publishing your data, typically of 0.8. If the object has a small amplitude, you could do something like 0.6. Because if it were 0.8, then you start to not see all the detail as well. So anyway, again, I'm using 0.6. But if you don't have any plots visible, again, choose Floating, and you'll be able to see all the data points. Okay, now it looks like I do have a little bit of scatter. So I'll go to this data point here. Again, that's going to go to my image viewer. You'll see it as I zoom in here. And it looks like the object passed in front of a star. So this is similar to what we saw before. So again, it's not uncommon if you have an object pass in front of a star. It's no big deal. Again, I'm just going to identify, it looks like image number 13. So 10 to 13 here. Select those, right click, choose delete. And now those have been removed from the raw plot. Now it says it's an unnamed object. Again, if you see that, one is you could give it a custom object label. You could do that. But in this case, it's because we haven't yet attached object data. So again, I mentioned doing that before. Give it the number or the name if you want. Click search, click OK. Now it has attached object data to that photometry set. And again, you can see that by all of these columns having been populated. Now the next step, again, we have 2 nights of data. So I can do graph, plot all sets, and you'll notice that they might not be 100% aligned. In other words, I'm suggesting that they might need an offset. You might need to offset this photometry set by some amount, and that's completely normal. Again, we used actually different comp stars. We used a different aperture, measuring aperture just a little bit smaller, and again, just some differences from one night to the next, and so that will result in an offset. That's perfectly fine. Because we have applied object data, it has a median magnitude. We can select both photometry sets here and choose auto offset absolute. So it's going to apply that, and now we can replot the data, and now they are lined up a little bit better. So that's good to know. Now that the 2 photometry sets are aligned from one night to the next, we can do our period search once more. Find period. Again, I'm using same search parameters as previous, and choose find period. Now this is quite good. So our first candidate here, 2.2598 hours, and that is very, very much in agreement with the published rotation period of, I believe it was 2.599 something. We're very much identical to the published rotation period. Now again, keep in mind these were nights of data prior to impact. So if you're watching this video at some later point in time, and now the published rotation period is somehow different, again, as a result of the impact, just keep that in mind. But it will likely still be very close to this. So 2.2599, very good result here. And this is actually a pretty challenging object because it has a very low amplitude. It has an amplitude of 0.1. That means you have to have very good signal-to-noise ratio on it. So keep that in mind. If you're starting out for the first time, then I suggest objects that have a higher amplitude, meaning that they would be less challenging. So there's actually a tool here. If you go to Tools, Lightcurve Database, then you can potentially do a search for all objects that have perhaps an amplitude of that you would want to work with. So maybe an amplitude from 1 to 2. You would clear out the object label, and maybe you would uncheck that and you'd click search. And what it will hopefully do for you then is return all of the asteroids that have an amplitude between 1 and 2. So that might give you some starting point, but there's others. Again, if you want to do more reading on this topic, feel free to do so. But either way, I hope that this video gives you some idea of the overall process involved, that this is, again, asteroid photometry is not the most straightforward because it is a moving object. You want to do light time correction, that's here. You want to do h minus g correction. So all these things, these are all quantities and values that can be computed by Tycho. So I hope to make it an easy process here. So as you see, we have very good data and we had a very good result. So that's about it for this video. Thank you for watching and see you next time.